Alright, so in this first example we have a beam that that has a pin support on the left hand side and a roller support on the right, and we'll mark them as point A for the pin support and point B for the roller support. Now the second thing that we need to understand is what kind of reaction forces and how many do we have. So the pin support will give us 2 reaction forces and the roller support will give us 1 reaction force. So let's write them down. Firstly, we have the horizontal reaction force in the pin support. Well, actually, let's also define the axis and which directions are positive. So we'll have as positive directions for the forces. If the force goes to the right, it's positive, and it will call it a x direction. And if the force moves to the downside, it's also positive, and the force will be called, or the direction will be called the z direction. So the first reaction force at the pin support is the horizontal reaction force Fxa, and this is equal to 0 because there is no horizontal force that is trying to move this beam to the horizontal direction. Secondly, we have a reaction force at point A, and we'll call it Faz. Thirdly, we have a reaction force at point B in the roller support, and this is a horizontal reaction force, and we'll call it Fbz. And we'll start our calculations from this force. So to find Fbz, we will use the sum of moments at point A, and we know this has to be equal to 0 because otherwise the structure will be unstable. Now for the equation, we don't have to count in the reaction forces at point A because they have no moment arm. It will be for the force Fxa, it will be 0 times 0, which is 0, and for the reaction force, it's some reaction force Faz times 0 is 0. So we'll start from the force in the left hand side of this 17 kilonewtons, and this 17 kilonewtons has a moment arm of 0.5 meters. Remember, a moment arm is something that needs to be perpendicular to the force and is the distance from the point at which we calculate the moments till the force. So in this case it's 0.5 meters. For the next member we'll have this distributed load, which is 12 kilonewton per meter. And firstly we need to multiply the distributed load with the distance of how much do we have this distributed load, and we can see we have 4.5 meters worth of this distributed load. This will give us a concentrated load, and we know that this concentrated load will be at the middle of the distributed load. So the moment arm that this distributed load has is 0.5 plus 4 plus 4.5 divided by 2, and that all equals up to 6.75 meters. Finally, we have for the known moments, we have the moment right at the end of the beam, 9 kilonewton meters moment. And since this moment is going counterclockwise and we marked all the rest of the forces that go clockwise as positive, this has to be a negative moment, the way we decided to mark it in our equation. And for the final member we have FBZ times its moment arm, and it's a negative moment because again it relative to point A it moves the beam counterclockwise. So FBZ minus FBZ times its moment arm, well actually there's one distance missing, it's this 1.5 meter distance from the start of the distributed load till the roller support. So 0.5 plus 4 plus 1.5 will give us 6 meters. And this whole equation is equal to 0. So now let's use our calculator to find out the magnitude of FBZ. So FBZ will be equal to 60.7 kilonewtons. Now let's move on to calculating our final unknown FAZ, and we will use the sum of forces in the Z direction because the only unknown force in the Z direction is now the reaction force FAZ, and we will have one equation for one unknown. Now for the first member we'll have the unknown reaction force FAZ, and according to the way we draw our axis, it is a negative force. For the second force we have this 17 kilonewton force, which is a positive force. Thirdly we have the distributed load times how much we have this distributed load, which is 4.5 meters. And finally the reaction force that we just calculated, 60.7 kilonewton reaction force, and that all has to add up to 0. So once again let's use our calculators to find out that FAZ is equal to 10.3 kilonewtons. Now let's move on to calculating our shear force diagram. And in the shear force diagram we care about forces that move in the vertical direction. The shear force diagram shows what is going on inside the beam. So when a reaction force is pushing the beam up, it will create a shear within the beam that has the opposite direction but the same magnitude. So according to our coordinate plane, positive forces will move to the down, and since FAZ moves up, it's a negative force, and it creates a positive shearing within the beam. So we'll have plus 10.3 kilonewton shear within the beam. Next up we have a force of 17 kilonewtons, and since this force is moving down, it will create a shearing within the beam that has the opposite direction, so it's a negative shearing, so it's 10.3 minus 17 kilonewtons, which will be equal to minus 6.7 kilonewtons. And as we move along the beam, we really don't have any other forces or reaction forces until this distributed load. So it will be just a horizontal line until this distributed load starts. And distributed loads will create a linearly growing or decreasing shear force diagrams, because the way you can think about it is you have a very small, let's say 1.2 kilonewton worth of concentrated load after each 0.5 meters, or however little amount of distance after however little amount of distance, and this will create like a small stair stepping where you have like 1.2 plus 1.2 plus 1.2, but we will just draw it as a linear line. Also, one thing that we need to remember is until this reaction force FBZ, we will have a linear diagram. So 12 times 1.5 meters minus 12 times 1.5 meters minus 6.7 is equal to 24.7. But now at this point we have the reaction force FBZ, which has a upwards direction, which means that it creates positive shearing. So minus 24.7 plus the reaction force, which is 60.7, will give us 36 kilonewton shearing within the beam at point B. And finally, we have the only horizontal force that we have left is this final part of the distributed load, which has the length of 3 meters, and 3 times 12 kilonewton per meter is equal to 36, and 36 minus 36 is equal to 0. Now let's move on to calculating moments diagram. And we know from the theory that there's two ways we can calculate the moments diagram. We can either cut the beam at points in which the moment diagram changes the directions, and then we will calculate the sum of moments for the cut either on that we will have on the left hand side or on the right hand side. Or the second way is integrating shear force diagram, and we will do the integration part. So when we integrate some function, we will essentially calculate the area of that function, and what will also change is the direction of the line. So when we have a horizontal line, this will change to a linear line. When we have a linear line, this will change to exponential line. So at point A, since we don't have any moment, the moment within the beam, the reaction moment within the beam will be equal to 0. So we'll start from 0. And we will calculate the first area, which is this positive area, which has the height of 10.3 kilonewtons and the base of 0.5 meters. So 10.3 times 0.5 is equal to 5.15 kilonewton meters. And since, as I pointed out previously, when we integrate a horizontal line, we will get a linear line. So this is what we will get. And let's also write down this 5.15 kilonewton meter moment. Secondly, we have the rectangle, this negative rectangle, up until the distributed load starts, and this will also create a linear graph, since the shear force graph has a horizontal line. And the area for this will be 6.7, which is the height, kilonewtons, times 4, which is the base, minus 5.15. And that will give us 21.65. Now let's move on to the third area, and the third one is a bit tricky. We will divide this area into one triangle and one rectangle. So first we'll start with the rectangle, the smaller rectangle. It has the base of 1.5 meters times the height, which is 6.7 kilonewtons, plus the area of this triangle, which has the height of 24.7 minus 6.7 kilonewtons, times its base, which is 1.5 meters again, and divided by 2 because of how we find the area of a triangle. And since the shear force is negative, we'll just put a negative sign. We'll just make this equation negative, and this will give us moment of 23.55 kilonewton meters. Previously we had our negative 21.65 kilonewton moment right where the distributed load part starts, and we will subtract from that this, or rather add to that, this negative 23.55, which will add up to 45.2 kilonewton meters. Now the final area, we have this huge triangle which has the height of 36 kilonewtons, a base of 3 meters, and we'll divide this by 2, which will give us an area of 54 kilonewton meters. And we will add to that our negative 45.2 kilonewton meter moment, which will give us a moment of 9 kilonewton meters right at the end of this distributed load. So 9 plus 9 kilonewton meters. And up until the end of the beam we will have pretty much nothing, and right at the end of the beam we will have this moment, which is 9 kilonewton moment. So 9 minus 9, because it moves counterclockwise, and we marked counterclockwise moments as negative, will give us 0.